But now we turn to an application of these algebraic properties and the null space. Now error-correcting codes are used in cell phones, flash drives, and many other devices. Hamming came up with a code that's now called a linear binary block code. Linear because it's based on linear algebra, binary because it uses zeros and ones, and block code because it encodes blocks of fixed length using the error-correcting code. But here's how a linear binary block code works. Suppose I want to send a message. Let's say my message is 4 bits. I encode that as a block of, in this case, 7 bits. Then I transmit it through what's abstracted as a noisy channel. This is a channel that sometimes introduces errors during transmission. At the other end of the noisy channel, a 7-bit block is received that might differ from the block that's injected into the channel. And then that's decoded, hopefully to obtain the original 4 bits that was transmitted. In a linear code, the block that's actually injected into the noisy channel is called a code word, and we'll denote it by C. The block that's received at the other end might not be a code word. We denote that by C tilde. We let big C denote the set of code words allowed. Now, Hamming's code was a linear code, and what that means is we represent the 4-bit and 7-bit blocks as 4 vectors and 7 vectors over GF2. We can write the 7-bit block that was received, C tilde, as C plus E. E is the error vector. Since we're using GF2, E has 1s precisely in the positions where C tilde differs from C. The key idea in a linear code is that the set of code words, big C, is the null space of a matrix H. The advantage of doing this is that it makes the receiver's job easier. Now, the receiver gets C tilde and needs to figure out what the error vector is. How can the receiver do that? The receiver multiplies C tilde by the matrix H. H times C tilde equals, substituting for C tilde, H times C plus E. And now, using one of our algebraic properties, we can split this sum up. H times C plus E is H times C plus H times E. Using the fact that the set of code words is precisely the null space of the matrix H, we know that H times C is the 0 vector. So we end up with just H times E. So the receiver can compute from C tilde the product of H times E, and from that needs to determine the error vector E. How can he do that? In Hamming's original code, this is the matrix H. Now, you might notice something interesting about the columns and the order. Well, suppose that the noisy channel introduces just 1-bit error. Then E, the error vector, has only 1, 1. The rest of its entries are 0. Can we determine the position of that bit from H times E? Let's say, for example, that E has a 1 in its 3rd position. So E looks like this. H times E is then using the linear combinations rule, H times E is then the 3rd column of H, which is 0, 1, 1. And that tells us where the error occurs. As long as E has at most 1-bit error, the position of that bit can be determined from the product H times E. This shows that the Hamming code allows the receiver to correct 1-bit errors.